welcome everybody. My name is Federico Benazzo. I am one of the co-chairs of this year's Caltech Space Challenge, along with Jen, who is outside waiting for one of our judges to arrive. So for those who don't know it, the Caltech Space Challenge is basically one of these competitions that have been started 15 years ago now, in 2011. And it's a student-organized competition that calls in 32 students from around the world to split them up into two teams of 16 students and basically give them 5 days to come up with a concept for a very challenging mission. And this year, we have found 32 of the brightest aerospace graduate students, and we've given them a tough mission that I'll go on to explain very soon. But today, we have a panel of 4 judges. 2 of them are right here in the front. Of Professor Watkins, who is a professor of aerospace and geophysics here at Caltech. He's the director of the Keck Institute of Space Studies that have been helping us a lot with organizing this. And he's also the former JPL director. We have Professor Hare. He's a professor in aerospace, focusing on control studies, and he's a senior research scientist and technical fellow at JPL. And here is Carol Raymond. She is our 3rd judge. She's a principal scientist at JPL and also deputy principal investigator for the DOM mission at JPL. And then he's going to be arriving a little bit late, but Garrett Reisman, professor of astronautics at USC, he's also going to be one of our judges. And this year's mission is a 2-in-1 mission. Basically, we have tasked the students to come up with a concept to both go and visit a heli-like comet that's nearing Venus orbit. The reason is because heli-like comets are kind of these time capsules that preserve water from the very, very early beginnings of our solar system. And then the second target, because of the vicinity to the comet, is going to be Venus, which is known to be a sort of Earth's sister planet, and is very important to study climate. And also, we're asking the students to come up with ideas to complement upcoming missions to Venus for the 2030s. So without further ado, I'm going to ask Team Voyager to come up and start the presentation.
Hi everyone, we're Team Voyager. Our mission is Seahorse, spectroscopy for escape of Venusian atmosphere and hydrogen outgassing in retrograde swan encounter. That's a long name. But yeah, we're really excited to be here. The mission we've designed, as Federico was saying, is a dual target mission, so comet flyby followed by Venus orbit insertion. And we're looking to address a couple of key decadal survey questions. Namely, what processes drive the dynamics and energetics of atmospheres on solid bodies like Venus? What processes govern atmospheric loss to space? And what controls the amount of available water on a body over time? And so it's really interesting to study both these inner solar system distinct bodies because there's a shared process, the volatile loss and the atmospheric escape to space. On comets, we see sublimation driving this process when the comet is approaching the sun. We have photodissociation happening and hydrogen escape. So lighter volatiles, we can look at isotopic ratios like deuterium to hydrogen and detect species like ions, neutral atoms, and try to characterize that atmospheric loss and the coupling with the solar wind. And in this way, we can start linking how the inventory of these volatiles is changing over time. And so Venus is also specifically interesting to us because in many ways it's like a sister planet to Earth, but there may have been a runaway greenhouse gas effect that caused a lot of the loss that we see in its atmosphere today. We do have a storied history of missions to both comets and to Venus. Impact missions like Deep Impact, as well as orbiting and landed missions. But this is really interesting because it's a Halley-type comet. We get to go close approach and then also go to Venus. And with Venus, yes, we have characterized atmospheric loss processes, profiles of temperature, pressure. We have upcoming missions like Veritas, as well as Da Vinci, which is going to send a probe in the Venusian atmosphere, tracking some of those upper atmospheric processes. But the time frame, the time scale of that mission is much shorter, whereas here we have a minimum 2-year orbital science campaign around Venus that can provide some long-term observations on atmospheric loss, as well as the coupling to solar wind and magnetic field variations. And yeah, we talked about this a little bit. So this is a really cool mission opportunity. SWAN is going to have a close approach in 2034 per the mission brief, so it's a very time-critical window for us. We have these new studies, these upcoming missions to Venus that should have happened by then. So Da Vinci and Veritas are slated for around 2030, 2031. So we have this window for synergistic mission science, which is kind of driving the need for our design. And with that, I'm going to talk a little bit. I'm still going to be talking about science and payload and how we're planning to optimize for this mission. Some of our key science objectives. So characterizing the physical chemical inventory and the activity of this comet, P2005T4 SWAN, as it's visiting the inner solar system, looking at the atmospheric escape of volatile, so all the way from the upper atmosphere to the ionosphere, magnetosphere, and beyond over that 2-year baseline I talked about, as well as characterizing the interplanetary dust and solar wind environment to contextualize some of the measurements that we do at Venus and at the comet flyby. So we are going to be doing measurements in the interplanetary cruise phase as well. This is a breakdown of some further refinement for the comet flyby phase. So we're going to look at the gross morphology. We have optical imagers. My friend is going to talk about payload. Looking at the local dust and plasma environment, as well as the particulate hazard, so the dusts. Venus orbit. We are going to be looking at atmospheric escape. This is going to be like upper atmosphere and beyond. Looking at the rate variability and solar wind dependence of atmospheric loss to space. And I already talked about interplanetary cruise phase. We have a lot of this mapped out further in the STM, and we're happy to take questions about it, but this is the high-level science requirements. With that, I'm going to hand it off to my colleague to talk about the spacecraft and kind of the plan of operations.
All right, hello everyone. Let's take a first look at the Seahorse hardware that's going to accomplish all of these science objectives and fulfill these requirements over the years, in addition to some secondary ones that we'll go through today. I'm going to briefly overview the science payloads that are on board 4 spacecraft that we'll discuss today. You'll get all of the engineering details your heart could desire over the next 45 minutes. But to give you a brief overview, the main spacecraft, the eponymous Seahorse, is really the workhorse instrument and hosts everything that we need to accomplish our main science objectives. Everything that you're seeing over here are probes that will be sent out during the comet flyby, are all secondary science and additional supporting measurements for the primary science case, but we'll accomplish everything just with the remote sensing and in situ payload instruments that are mounted on the main spacecraft. That includes, as mentioned, optical imaging, UV spectroscopy, and a suite of in situ measurements for magnetic and electric fields, solar wind, and mass spectrometry along the way. To give you an overview of the specifics on the remote sensing side, which is what the vast majority of the measurements made across the mission will be, we have a three optical imager suite of a telescope at 0.25 degree field of view. This is well matched to the expected nucleus size of the P2005 comet as we fly by, so we'll get surface morphology and general size and shape of the nucleus as we're going past, as well as a 1 degree and 12 degree imagers that are sized to get broad sweeping morphology measurements of the dust tail, ion tail, and coma from millions of miles out or millions of kilometers out up until the closest approach. The UV spectrograph is going to really be returning all of the volatile information and spectroscopy abundances that are going to bring most of our science goals home. And then we also have a hydrogen imager specifically placed on the Fry-1 satellite. That's the closest probe passing towards the nucleus of the comet. And that is specifically a narrowband UV imager targeting neutral hydrogen that was just photoionized from the comet's surface and water. For in situ instrumentation, we're essentially taking measurements the whole way through the mission. That's in interplanetary space, through the comet flyby, and in the Venusian atmosphere. We're getting solar wind information, magnetic field, electric field, and general ion volatile spectroscopy throughout the whole mission that allows us to link all of these individual environments and answer big picture questions about the formation of our solar system as well as its current evolutionary state. We're also getting dust physical measurements from the comet coma as we're passing through, telling us about the size, shape, and distribution of dust impactors as we pass through that area and connecting it to the interplanetary science that we're doing as well. And we also have 2 experimental payloads that will be discussed in great detail throughout this. The first one is the SALT impactor system. You saw that we have 2 probes named Fry. Those are the children of Seahorse. And with your fries, you always need salt. So we have the SALT impactors. This is essentially a few thousand small 2.5 gram impactors that essentially simulate pebble accretion, which is how we expect planetary bodies and comets to be forming in the early solar system, as well as to dominate the majority of the impactors that long period comets see whenever they come back through the ecliptic, as P2005 is doing right now. We're leveraging the really fast relative velocity that we have on the ascending node of the comet when we fly by to essentially throw 5 sticks of TNT with any single pellet at the comet that hits, and this allows us to see the below surface layer composition in the remote sensing UV spectroscopy after we fly by to understand how the comet exists, in 3D space rather than just on the surface.
So now I'm going to talk a little bit more about the kind of aside onto these payloads, since the rest of our presentation is focused on our main Seahorse. So all 3 of our payloads here, the SALT, Fry 1, Fry 2, all fit inside the same boxes for manufacturing simplicity, and they all use the exact same components. These do not have propulsion. They have stick-off control using reaction wheels and get their attitude using star trackers and inertial measurement unit. And on board each of them, they have different science payloads to get dust density, hydrogen density, its composition, and magnetic field measurements. So using the SMAD, we were able to find that this type of payload will probably fit within a 20 to 25 kilogram mass budget. Looking a little bit deeper into how this is going to occur, the comet is going to pass the ecliptic at around February 25th, 2034. We are going to have clamp bands that are going to release these payloads at about 1 meter per second, and these are going to be equally spaced apart, so about 2 weeks before our impact, we're going to release all of our salts, then our Fry 1, Fry 2, and about a day before the impact event is going to occur, we're going to have the grains release and then spread and cover the entirety of the field of view for the SALT impactor. At T0, we're going to have impact, and since the solar wind blows these ions very quickly, anywhere between 250 kilometers per second to 800 kilometers per second, at 2 seconds after impact, all the ions will have blown downwind and have passed beyond, shown here in the red lines, where our anticipated Seahorse is going to pass through. At around 3 seconds, Fry 1 will then pass through, and at 6 seconds, Fry 2 will pass through, giving us really important information, and I think this has never been done before in any sort of comet or Medusan mission.
This was the first technology demonstration that we're planning to do. We are also planning to do a second technology demonstration after we finished all the science requirements that we are doing, so after the 2 years in the orbit of Venus. So I'm not sure if you're familiar with atmospheric breathing electric propulsion systems, but the idea is that you basically take the atmosphere of a planet as propellant. There are some systems out there, you can use different thrusters. This is just a schematic. We would use a Hall thruster as thruster system, and we would like to use the Venus's atmosphere as propellant. So studies have been done, nothing has, or only one has flown 20 years ago, but there are missions out that will fly in a few years, and there has been a lot of studies referring Earth atmosphere used as propellant. And we compared the density between Venus and Earth, and theoretically this could also work at Venus, and Venus has the high advantage of using CO2 instead of N2 as the main factor, which would be more effective for a Hall thruster. And with this design we would get a resulting propellant mass flow of 2.2 milligram per second, which is one of the lower requirements for a thruster that he could do. And we are planning to use a diffuse intake that we're just taking and doing this technology demonstration at the end of the 2 years.
Now we're going to talk more about the broad high-level mission architecture. So you're going to see this slide a couple more times, so don't worry about taking all in, but practically we're going to have launch, an interplanetary cruise stage to reach our comet. We perform our flyby and our salt and fry deployment. Then we have another interplanetary cruise stage before we do Venus orbital insertion, and then we have our 2-year monitoring orbit around Venus. Let's start with launch. So our launch date is May 9th as the center of a 2-month launch window. After launch and our payload separation, a separation switch is going to close the circuit on our primary batteries, of which we have 2 redundant primary batteries. During the 1 hour in which these primary batteries are in service, we will perform initial attitude acquisition using our star trackers and point ourselves towards the sun. Then we're going to deploy our solar arrays, establish link to ground stations, and then we can perform our system checkouts. Our entire payload can fit within a Falcon 9 on a Cape Topper configuration. During the interplanetary cruise, once our systems have been checked out, we can then start performing some science, such as measuring the interplanetary ions, dust, and plasma environment. During the cruise phase, we're using our H10 Hall effect thrusters, and during this time, we're also using our wide field and narrow field imagers to get precision orbit determination of our comet and perform some course corrections to make sure that we're intercepting the comet at the desired distances. Once we are then at our comet flyby, we're going to deploy our salts and our fries, like I mentioned previously, and then we're going to not only get the remote sensing and in situ data from those salts and fries, we're also going to be using the Seahorse to take much more wide view pictures and scientific data. Then again, we have another cruise and course correction phase, performing more science on the inner solar system environment. Before we get to Venus around late 2034, we are going to perform 7 aerobrakes around Venusian orbit with a periapsis of 140 kilometers above the Venusian surface. Then once we have reached our desired apoapsis, we're then going to perform a periapsis raise to reach our desired final orbit, 250 kilometers from the surface to about 60,000 kilometers, so a high elliptical orbit in a polar inclination. At this point, we have already been established communications, but even at our worst case scenario at Earth-Venus opposition, we still have a signal-to-noise ratio of 7 dB. During our 2-year mission, we have a budgeted 370 meters per second of propellant for station keeping, although we only need about 70 meters per second based on our current calculations. And during this time, we again perform all of our science experiments, and at the end of our mission lifetime, we will then dip the Seahorse into the upper atmosphere to perform the ABEP demo. Here is a list of our critical requirements to make sure that our mission can function. So not expecting you to be able to take it all in, but looking on the left side, we have some of our most critical requirements for all our different subsystems, and our compliance is showing positive margin on all of them. And now we're going to transition into mission design.
Okay, so these are our trajectory requirements, our high level. So one of the main ones is that we wanted to ensure a relative velocity of the comet that is less than or equal to 85 kilometers per second. This was set by the instruments that we have on board. We also wanted to make sure that our closest approach to the comet was at least 1,000 kilometers, so we don't accidentally hit it. And also establishing a bound elliptical orbit about Venus, since that stems from one of our higher level requirements to stay in an operational orbit for 2 years. So Comet Swan is pretty interesting. Unfortunately, not much is known about its orbit. It's very uncertain. It is a retrograde orbit, so it's a very high inclination, a large orbital period. We don't see it but once every 27 or 28 years. It's going to come very close to our sun and to Venus in 2034 at its ascending node, and at this time the activity on the comet will be very high. So these are the launch characteristics that we have determined would suit our mission. Our launch date would be May 9th of 2031 on a Falcon 9. Our declination of the launch asymptote has allowed us to fly out of Kennedy Space Center with a C3 of 4.21 and a maximum launch mass at that C3 of 2,800 kilograms, which is higher than what our spacecraft mass comes in at.
So yeah, continuing with the trajectory analysis, as we sort of stated earlier, we are anticipating a launch in a window of May 2031, a comet flyby in early 2034, and our final arrival at Venus at the end of 2034. So to talk about how we plan this trajectory, I'll just start off by sort of a trade analysis that we did. We started by looking at the different gravity assists and Lambert arcs that we could achieve and their resulting delta V and time of flight comparisons. And we found a family of solutions that essentially just consists pretty simply of a departure from Earth followed by intercepting the Swan comet and then finally arriving at Swan. So not actually performing any gravity assist to do this. And we located a solution that consisted of around 6.5 kilometers per second, including departure velocity. And from that, we took this trajectory as an initial guess for a low thrust scheme and developed our low thrust transfer profile, which consists of departing from Earth, intercepting the comet, and then intercepting Venus. And we see here that we achieve an interplanetary delta V of around 4.7 kilometers per second using a propulsion system that consists of a maximum of 155 millinewtons of thrust. Continuing onward, we can see here the actual profile of the trajectory. So as I mentioned, we depart in 2031, and we perform 3 revolutions about the sun before we eventually intercept the comet. And you can see we have several thrust arcs occurring here before we intercept Venus. And we should note as well that we have margin actually in terms of the amount of thrust we can achieve with our propulsion system, which allows us to perform corrections as we anticipate the ephemerides improving over time as the uncertainty of the comet position decreases.
Okay, and so since we were doing a low thrust trajectory, we wanted to use aerobraking to get into our final orbit at Venus. So our Venus arrival v infinity is roughly 0 on a parabolic orbit. Our number of aerobraking passes roughly between 5 and 10, so maybe a month to get down to our final orbit. And then we'll have to do a small periapsis raise to get to our final orbit of 250 kilometers, and then our apoapsis is 60,000. And then another thing to note is that Venus Express noticed that the periapsis of their orbit had to be changed as they went around the planet because of solar perturbations. So there's only a little bit of maintenance that we would have to do to keep our orbit in the right spot. So this is our final orbit, again, 250 by 60,000. Every revolution is about 21 hours, and our max eclipse time is 3.9 hours. And again, this was a very similar final orbit that the Venus Express mission had. So being down in the soup at 250 kilometers will let us get all those good atmospheric measurements, but we'll also make sure that our spacecraft doesn't burn up because of the heat. And then this probably should have gone in a different part of the presentation, but I wanted to add that since our relative velocity to the comet is about 80 kilometers per second, and we are planning to throw impactors at it, we want to make sure that we aren't breaking apart the comet. So there's a lot of uncertainty in the density and the size of the comet. So I wanted to run a quick analysis, and this just shows that no matter what the radius is within what has already been established, what is already known of it, and the potential densities of the comet, our small impactors will not even risk fragmenting the comet, so no worries there. And with that, we will move on to propulsion.
Thank you. So you just saw the delta V, basically, that was given to me. And next to the delta V, I also had the thrust requirement that they were using for their thrust trajectories. So there was a minimum of 155 millinewton. One of the other requirements was that like a high cumulative time of thrusting is required for this mission, because we have a very long orbit time, like 3.5 years until we reach Venus, then 2 years of operation, and then afterwards the ABAP. And additionally, of course, we have the limitation of power with the electric propulsion system. We need 3 kilowatt for achieving the 100, like the 3 kilowatt was the maximum that we can use at 1 AU to still have like good structure. So you already seen this picture, just quick recap. So the propulsion phases are separated in 4 phases. Using the launch energy doesn't require the electric propulsion system to work. Then the interplanetary trajectory. Then the aerobraking does also not require the electric propulsion system to work. And then in the end, we again use the system for station keeping. Just a quick trade-off between a chemical propulsion system and the electrical propulsion system. So with a chemical propulsion system and impulsive maneuvers, we could reduce the delta V that we're needing to 4.0 kilometers per second. And for the low thrust variant that we are doing now, we have a delta V of 4.7 kilometers per second. But as you can see, like the specific impulse of the electrical propulsion system is really high. So in the end, we have a really low propellant mass compared to the chemical propulsion system. And also the flight time does not distinguish too much. And at the orbit at Venus, we have a very high excessive energy. So because we're not flying further across than 1 AU, it makes sense to use solar electric propulsion as propellant. So as already mentioned, we were choosing the Hall thruster H10 as our propulsion system. We're carrying 2 on board, one for like the second one for redundancy. We can throttle the operation between 750 watt and 10 kilowatt, but as already mentioned, we need the 3 kilowatt operation mainly. And right now there are 2 different options shown for 3 kilowatt, one low voltage and one high voltage condition. One gives us the minimum required thrust of 155 millinewton with 2,200 seconds of ISP, and the other one gives us a 194 millinewton thrust with ISP of 1,820 seconds. And we were like, because we need 155 millinewton, we can theoretically use it, but we don't have a margin. So for this estimation, we were using the worst case of the ISP of 1,800. And as we are getting closer to Venus, of course, we are getting more energy that is allocated to the solar electric propulsion. So we also get like up to 5 kilowatt that we can use at Venus. And this is just an overview of the delta V and propellant mass that we're using for the 4 mentioned phases. So none for the aerobraking, of course, and a total of 330 kilogram for the way to Venus. And after that, it's just like not so high. We were estimating 300 meters per second delta V for the station keeping, and that gives us a total of 5 kilometers per second delta V and a total propellant mass of xenon of 353 kilogram. With that, I'm giving over to Simon.
Hello, everybody. I will today present you and guide you through our guidance, navigation, and control subsystem. And first of all, regarding requirements, the main important part here is that we want a GNC subsystem that is able to control our spacecraft over 3 rotational and 3 translational axes. Our aspect, which is super important, is that we want to pass near our comet at approximately 1,000 kilometers, which will result in a very high slew. The pointing accuracy that we need during the comet interception is roughly 3 millirads, and for the pointing accuracy during the Venus operations is approximately 0.1 degrees. So first of all, I want to mention that the GNC system has different types of autonomy, during different phases of the missions. So basically, during phase 1 and phase 3, we would like to reduce as much the autonomy of the GNC and navigate and command only through ground-based commands and navigation parts. Phase number 2 is the most challenging for the GNC subsystem, and here we want as much autonomy as possible. That's why we would like to implement some image processing techniques with camera for detecting and tracking the comet. And for the last phase, in which we will operate in Venus orbit, it's important to have some good AOCS autonomous part, in which we can communicate and make the science we are required. So in terms of sensors, here are the sensors we selected for our system. Basically, we'll have 2 navigation cameras that will be used only in the closest approach, in combination with IMU in order to get like inertial measurement data. Also, the star trackers, we decided to use 3 of them in order to get like attitude, absolute pointings, and to have some redundancy if they are blinded by anything like sun or the comet coma. Some sensors, these are basically designed used in order to recover from any eventual contingency, like in safe modes. In terms of control, we are thinking to use the reaction wheels, 4 of them, in order to perform the slews. Unfortunately, reaction wheels need to be desaturated, and this wise, we also integrated some reaction control thrusters. Mainly, during comet interception phase, here we make some simulations in order to show what would be the required angular velocity and angular acceleration during the closest approach. We basically simulated what would happen with our pointing during these phases. And the navigation that we computed a pointing budget in order to understand if we are able to achieve the performance, the pointing that is needed during the closest approach. And basically with the pointing budget we did, we achieved a pointing knowledge with approximately 2.09 millirads. And the basic idea, in order to overcome this angular momentum, we can use reaction wheels of 100 Newton meters second. And in order for the last boost, in which we need this kind of acceleration, we would like to use the thruster. And this will for the RCT maneuver. And this will basically boost our fast angular acceleration and will make the capability of imaging the comet longer. The next part, during Venus operation phase, here the most important part is basically to make science experiments and slew to the Earth and back. So basically we consider for our reaction wheel sizing and RCT sizing as well as mass need that we'll need for the saturation. So basically computed the control that we will need for this part. And one important thing that I would like to mention, that during one orbit we will approximately accumulate an angular momentum of 11.3 Newton meters seconds, which is basically considering all the perturbation that could occur, considering also the perturbation from the sun, gravity, and also from the Venus G2, or also the solar radiation pressure. So that's why we included a big margin here. And as is presented here, so the reaction wheel will saturate at approximately 8.8 orbits, which will definitely need to desaturate. So basically the propellant was sized in order to keep the operation viable through 2 years. Thank you. No, it's not ready.
Okay, cool. I'm going to be talking about the structure and a little bit later the thermal as well. So we have a couple of requirements for our structure. The first of which is our launch environment, which is the most harsh environment during our full mission. So we have quasi-static accelerations, we have resonant frequencies with the launcher, sinusoidal loading, shocks from deployment, the acoustic environment inside of the fairing, and then of course we also need to be able to interface with the launcher, and those are our launch requirements. And then within our cruise phase we need to make sure that thermally we're sound, that we're deploying all of the structures that we want to be, and that we're protecting against the debris of the comet. And then finally, once we arrive at Venus, we want to make sure that we're able to survive the thermal and the aero loads as well. So over the course of the few days, we went about making a CAD model, taking in all of the subsystems from all of the teams, generating CAD models, and then placing it within the main spacecraft structure. So we have our solar arrays, which take up a large area, and then the main structure is a carbon fiber sandwich panel, which we will use for rigidity. And then inside we have all of our instrumentation, our comms, and our pressure vessel, our thrusters, everything's in there. So for the propellant tanks, we spoke about how we're using xenon. we performed an early trade study of whether we should do metallic tanks or COPVs, so carbon overwrap pressure vessels, and we get a significant mass saving if we use COPVs. Using a operating pressure of 150 bar, we were able to size the propellant tanks to get the liner and the carbon thickness. Next, we decided to create a Whipple shield system, but during the Whipple shield design phase, it became obvious that the potential thin membrane, which is quite wide, would likely struggle in the launch environment. So instead, we transitioned to an aluminium foam sandwich panel construction, which would do much better in terms of resonant modes. And that is what we stuck with. So we took a bit of a mass penalty, but now we have some shielding, so that's important. We did a very basic FE model of the primary spacecraft structure, so the sandwich panels, just to see what our resonant modes were, where they were, and to get a rough order of magnitude of what level they were at. And we came in at about 30 hertz, which is above the 25 hertz requirement of Falcon 9. But obviously, we'd need further analysis to make sure that this result is verified. So then moving on to thermal design, our main thermal critical cases were when we're around Venus. That's because we're closer to the sun, and also Venus has a very high albedo. So our solar constant and our albedo were very high. We're also performing an aero capture maneuver, which meant that we had to derive a pressure model for Venus's atmosphere, which we could then use as an input into our heat model. And then, of course, we also have the heat from the subsystems inside. And in order to manage all of this, we have radiators on the backsides of the solar arrays, and we have our hot case when we're at our periapsis in the sunlight, and then the cold case when we're in the eclipse at the apoapsis. So some mitigating measures that we took, so the spacecraft is covered in MLI, and then we also have the radiators on the back of the solar arrays, which are connected to heat pipes so that we can take all of the heat from the main bus and dump it into those radiators, which also have passive bimetallic louvers on the back to basically modulate the emissivity of these radiators. So we did a static analysis for the hot and cold case where we got the instantaneous temperature, and then we also did a transient model for when we're in our 2-year orbit around Venus. And we're well within margins, which is very nice.
So I'm the responsible of the communication part of the mission. Of course, also for the communication, we have a bunch of drivers that we want to fulfill. Some of them are having a two-way communication between the Earth and the spacecraft. We have to take into consideration also a one-way downlink from the probes to the spacecraft to assure the TT&C and science delivery of the capacity, and also to have a communication in safe mode. I thought that a representation like this would have been more clear than just numbers. So basically what you can see here is that during the mission we identified 3 critical phases where we need to have to close our link budget. First of all, on the left we can see that we have the satellite, which is in the cruise phase, already launched, and is communicating with the Earth with a low-gain antenna on board. Meanwhile, on the Earth, we have DSN, so the Deep Space Network. I want to say that all the communication were done in X-band, and the choice of the X-band is due to a long heritage of previous space mission that were using X-band, and also on the use the Deep Space Network, which, as we know, as a station all around the world, we went a bit deeper in the scheduling part because we know that it's very crowded as a network. And will be very fast here. Just one point I want to raise is that the station, the antenna available can be of 34 or 70 meter bigger as a dish. And all the link budgets we closed were conservative with the 34 dish antenna. For what concern the antennas that we have on the spacecraft, as I cited before, we have a low gain antenna and a high gain antenna. The low gain antenna was for the first phase of the mission, and we have a very ideal radiation pattern on the bottom that can visualize better what are the main properties of this antenna. We have the low gain antenna where we can see that the main beam is much wider. Meanwhile, on the high gain antenna, which will be the one we will use for the communication when we will be in Venus, which have a much narrower main beam, so there will be a pointing study to do also on that. Some more data on this. It's the same power, transmission power we use it. And for the low gain antenna, we will see one more specification, which is more clear when we analyze the link that we have with the probes launched towards the comet. Here we have on the left the antenna we choose to put on the probes. It's a very simple antenna. It's a patch antenna, works in X-band. In that case, it's a one-element antenna, so the radiation pattern is very wide, almost omnidirectional, we can say. We can see 74 degree of half power beam width. And the application is quite interesting because we don't communicate from the mothership towards the probe, but there is just a downlink from the probe which collects the data towards the mothership. And since we don't know exactly the position of the probe, we designed a low gain antenna in a dual polarization, such that each probe communicated with the right hand or left hand circular polarization, so that if they are in the same line of sight, there is no problem of interference. In closing the link budgets, there were several criticalities. This is the link in the worst case scenario where we have the max distance between the Earth and Venus. We were able to close the link also in downlink, so from the spacecraft to the Earth at 1.6 dB, which is not a lot, but at least it was closed and is already conservative with the 34 dish on the ground. And I just want to show just a bunch of parameters that in the link budget were critical and required a trade-off with the other member of the teams for the calculation of the SNR. For example, the diameter of the antenna on the satellite. At the end, we end up with a dish of 2.5 meter, and it was a trade-off with the one with the responsible of the structure of the satellite. There was a question on the visibility time. The satellite is not always facing the Earth, and sometimes it's also in eclipse. And then, from what concerned the link with the probes, there was a problem of pointing, because, and this is also why we choose the low gain antenna. One thing I want to add here is that we are able to reach an SNR of 5 dB, taking into account also some margin of an error of plus minus 8 degree of pointing. And after this, I can pass the word to the power.
Thank you very much. So in the case of the power, our customers were all the subsystems that you saw before. And basically what we did was to collect which subsystems would be active, in which phase of the mission, and what would be their power consumption, their energy requirement, and we came basically with the worst cases and the limiting cases for our design. So especially the first launch and early orbit phase, which requires a lot of power, and also the safe mode, which we don't have any power from the solar arrays, and we need to survive with our batteries. So these were basically the two main requirements of our EPS design, which was to provide a power positive state when we have the highest power consumption at the beginning, and also to survive the eclipse with just the batteries. So in the case of the solar array sizing, driven by the first requirement, we came up with a solar array area of 16.5 meters squared. We have a margin and we bring it up to 18 meters squared. So that means two lateral solar array pieces of 4.5 by 2 meters. And then in the case of the battery sizing, with a depth of discharge of 35%, with the maximum duration of the eclipse from the SDK simulation of roughly 4 hours, we came up with a 1.5 kilowatt hour battery capacity, which is very similar to what flew on the Venus Express, so we would take the same heritage devices.
Now we'll talk about what we did over the past 5 days and what may happen if this mission were to be funded. So we started with the SMAD, like we all know, and we took at some heritage missions and looked at what a payload-driven mass allocation may look like. All of our systems, as you heard, all have margin built in, but we decided to add an additional 25 contingency over margin, leaving us with a mass at launch of about 1,400 kilograms. Once we had our initial budgets, then we broke this down into different sub-teams. So days 0 and 1, we split into science and trajectory and overall mission design. And over the next few days, we started splitting up even a little bit further into our individual subsystems, systems engineering, and risk analysis. Here's what an engineering timeline may look like. It's very constrained because we only have 6 years after if we started tomorrow before launch is going to occur. So in order to bring our timeline a little bit closer, we're using all high heritage trajectories, instruments, using instruments as is, for example, and therefore we're able to meet our launch window. We collected risks from all our different subsystems. We had every subsystem give us a list of their top 10 risks, and then we compiled the top 12 into here, and we looked at different mitigation strategies. So our top 3 biggest risks, even after mitigation, are going to be dust impact, which we're mitigating with the Whipple shield, loss of attitude by using diagnostic sensors, automatic recovery, and watchdog timers in case the instrument's not talking to us, and also ion tail charging, so we're going to mitigate that through grounding, coatings, and Kevlar blankets. And looking at overall mission cost based on, again, the SMAD, we found that the total mission cost is anywhere between $1.4 to $2.1 billion. And there are ways to bring this down, at least for the budget on the NASA side, by using a cake topper configuration, tech demos like the ABEP, and joint ventures with other agencies.
Okay, wonderful. Thanks so much. With that, I'd like to conclude and invite the entire team to come on up for Q&A. Thank you all.